Hello and welcome to another WJEC A level physics question. This time it's question 3 from January 2014's Unit 2 paper. And we're told that we've got two sources S1 and S2 and they're oscillating in phase, and we've got to start by explaining what we mean by oscillating in phase. So here we're just going to say that the sources are at the same point in their cycle at the same time. So basically they could be at the highest point at the same time, the lowest point at the same time, passing through the centre in the same direction at the same time, and so on. Next we're told that for constructive interference at some point P, as in the diagram here, of the waves from S1 and S2, the path difference has to be 0, 1 wavelength, 2 wavelengths, 3 wavelengths, and so on. We've got to state what's meant by the path difference, add into the diagram if it helps. So I've just labelled here lines from S1 to P and S2 to P, and the path difference, I'm just going to call it PD, is simply the difference in those two distances. So it's S2P, take away S1P. Next, the two sources are placed side by side as we can see in the diagram, and they're emitting wavelengths of wavelength 12 millimeters. And we've got to work out whether there's constructive or destructive interference at this point Q. Well, this 300 millimeters is a bit of a red herring, to be honest, because what we're really interested in is the path difference, and hopefully we can see from the diagram that because the distance from S1 to S2 is 36 millimeters, then the waves are 36 millimeters closer to S2 than S1 when they arrive at Q. So in other words, our path difference is 36 millimeters. Now let's take that 36 millimeters and divide it by the wavelength, which was 12 millimeters, and that will give us an answer of 3 wavelengths. And as we've seen earlier, if we have an integer number of wavelengths to the path difference, we get constructive interference. Next we've got to discuss whether or not the signal strengths observed at Q would vary if the detector will move to the right from Q. Well, as I mentioned earlier, the 300 millimeters is a red herring because the path difference is still 36 millimeters. So the detector will record a maximum. It's still constructive interference, in other words. However, the further we get away from the sources, the weaker the signal will be. And that's simply because as the waves spread out in space, they're spreading out over larger and larger areas and becoming less and less intense. Next, the microwave sources are arranged as in the next diagram, and the detectors moved along the line AB. And we're going to use our double-slit interference equation to determine the approximate spacing between the points of maximum microwave intensity. So our equation is lambda equals A delta Y over D, but here we're trying to find the spacing between the maxima, which is delta Y. So delta Y is lambda D over A. So delta Y is going to be the wavelength of 12 millimeters. Times D, the distance between the slits and the screen of 360 millimeters, divided by the separation of the sources, which is 36 millimeters. Now notice each of those units is in millimeters, so all I need to remember here is that the answer is going to be in millimeters. There's no real need to convert between units. 36 divides into 360 10 times, so hopefully we can easily see that this fringe spacing, as it's known, is 300. Let's get it right, is 120 millimeters. For the next part of the question, we've got an array of those in-phase sources lined up so that they're producing an interference pattern similar to that of the diffraction grating. And we can see that the waves are still a wavelength of 12 millimeters, and here the sources are 30 millimeters apart. We've got to find all the angles to the normal at which the beam maxima can occur. Well, first of all, there's always going to be a maximum in the straight through position at an angle of 0 degrees, so I'm just going to put that one down first of all. That's what we call the 0th order beam. Now the diffraction grating formula is n lambda is d sine theta. So if we rearrange that, we will get that theta is sine minus 1 of n lambda over d. So the first order beam will be found at an angle of sine to minus 1 of first order, so 1, wavelength of 12, separation of the slits effectively that they are of 30 degrees. And if we put that into a calculator, we get about 23.5, so let's call it 24 degrees. For the second order, we will get sine minus 1 of 2 times 12 over 30. And again, if we put those into a calculator, we'll find that we get about 53 degrees there. For the third order, the workings would be sine minus 1 of 3 times 12 over 30, or 36 over 30. And remember that sine functions have a maximum value of 1, so this answer is not possible. So finally, what we're going to say is that we're going to get beams at 0 degrees, a straight through beam, the 0th order, plus or minus 24 degrees, so 24 degrees above and below the horizontal, and plus or minus 53 degrees above and below the horizontal. Thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.